Hey y'all, I'm David, and this is Physics 2211 Lab 3, Black Holes. Okay, so for our introduction, part one of the lab, we were supposed to determine the mass of the black hole based on the motion of the star, and then part two, we're supposed to find an initial velocity that would allow our spaceship to orbit a moon without crashing while the moon is orbiting the planet. So, just a quick preview of the results. For the mass of the black hole, we ended up getting 1.31 times 10 to the 34th kilograms. Our FNet parallel was this line, our FNet perpendicular was this line, and our DPDT was this line. And as you can see, it's the same as the FNet perpendicular. For part one, our system was the star, and our surroundings were the black hole and the empty space around them. And for part two, our velocity was negative 500, 950, and then 0. Our system was the spaceship, and our surroundings were the moon, the planet, and then the empty space as well. Our fundamental principles for this lab were Newton's second law and gravitational force. And the models we used were position update formula, the velocity update formula, and the gravitational force formula. Okay. So for part one, this was the result. As you can see, our star is orbiting the black hole, and the forces are largest when it is closest to the black hole. And then here's the code. Over here, we have what I use to get the arrows to show the magnitude of the forces. We have our initial conditions, and then over here, we have our velocity update formula and our position update formula, as well as our calculated net force, our DPDT, and our net force in the perpendicular direction. And we're printing the mass of the black hole. And then I later used the average of the masses that were calculated in order to find a general mass for the black hole. And then here is the simulation for part two. So as you can see, our moon is orbiting the planet, and our ship is in some way orbiting the moon. It didn't crash into the moon. Yeah. And here's the code for that. So over here, we have our initial conditions, and basically I guessed and checked the speed of the ship until it didn't crash into the moon, and it somewhat orbited it, at least in the first 100 hours. And then over here, we have our position for the moon in relation to the planet, and the velocity and position of the ship. So the potential error for this lab mainly came from guessing and checking the velocity of the spaceship in order to get it to orbit the moon. Because we were only working in like 100-hour period, we couldn't completely determine if the spaceship orbited or not. But based on the video, it looked like it was on track to orbit the moon. How are the net forces and its parallel and perpendicular components different from the rate of change of momentum? For the net force on the system, we're looking at the outside forces that are acting upon our system and the perpendicular and parallel components of it. While when we're studying the change in momentum, we're looking at the change in motion due to those outside forces rather than just looking at the forces. If we wanted to predict the motion of the entire system, what would we need to include on our computational model? And would there be any dominant interactions? So what we need to include to predict the motion of the entire system are things such as the initial motion of the object, the initial velocity of the object, and the forces and interactions from the surroundings. Dominant interactions would occur in this situation based on qualities such as mass of whatever it is that's interacting with our systems. So, for example, the gravitational force of a black hole would be a dominant force compared to the gravitational force of something like a tennis ball. Yeah, thank you.